Okay, let's get going. I'm just letting you know I'm leaving my phone on because I might get a phone call that I need to take. So if it does ring, I'll just step out of class real quick. All right. Y'all ready to finish this up? Yeah? 2 more classes and then finals. I've started to started to think about the final. So I'm hoping that I'll have an opportunity to discuss that for a few minutes at the end of class today, and then hopefully next class we can spend some time on talking about it also. Let's get rolling here. We were calculating flux last time, and we had several formulas. So we're going to kind of pick up where we left off. All right. So go ahead and read through this. Find the flux of a vector field, f of x, y, z equals 0, y, negative z across the surface S, where S is part of the paraboloid, y equals x squared plus z squared, with y between 0 and 1, and then the disk x squared plus z squared less than or equal to 1 with y equal to 1. Okay, what? All right, so we need to first get a good understanding of what we're looking at, and I have the picture down there, but that's kind of cheating. If you didn't have that, right, you would need to figure out what this looks like on your own. Let me remind you of the formulas we had from last class. Quite a few of them. I did update Canvas. I realized that the Chapter 13 summary that has all the different formulas on it wasn't there, so I put those up, I think, on Friday or Thursday or something like that. It's a lot of pages, right? Yeah. Okay, so over here on the side, I'm going to write down the formulas that we have. The double integral over S of the vector field F dot ds. This is flux, all right? This is equal to double integral over S of F dot normal vector ds. Notice that we no longer have the vector on the S. Okay, so if you take your vector field and dot it with a unit normal vector, so this is the unit normal vector for your surface, then this formula is equivalent to this. But this is also equal to double integral over d of f dot ru, r sub u cross r sub v dA. So if you don't want to mess with the normal vector of the surface, then what you can do is come up with the parametric representation of the surface. That means your function r of uv that draws the surface. Do the partial derivatives, cross product, then dot that with your vector field. And then there were 3 special cases. Okay, so this is also equivalent to if z is a function of x and y, then this becomes the double integral over d of, let me make sure I write this down right, p, negative p, times partial of g with respect to x minus q, partial of g with respect to y, plus r, all of that dA. And there were 2 more after that for the other 2 special cases. All right? Okay. So here we go. We have a vector field. So here's our vector field, PQR, across this surface S, where the surface is actually 2 surfaces. It's part of a paraboloid, y equals x squared plus z squared. So you have to understand that that looks like a bowl that opens sideways out the y-axis. All right, so you have to kind of remember that when we were covering quadratic surfaces. It also gives you a restriction that the y-coordinate is between 0 and 1. So we're looking at something like, if this is x, this is y, this is z. It's coming out the y-axis. It's this bowl-looking thing, like this. Okay, it's a paraboloid coming out like this. And then the y values are stuck between 0 and 1, so it stops here. Okay? That's what this first part's saying. Then you have a disk, x squared plus z squared equals less than or equal to 1. That is a circle that is parallel to the xz plane, because the y coordinate, right, it doesn't appear here. But then it says we fix the y coordinate 1. So we're actually going to move the y coordinate out to 1 and then draw a circle, all the circles with the radius less than or equal to 1. So that creates your disk here, your basically your outer surface right here. Okay, so that all that information really turns into this thing right here. Okay? So this is our surface, and what we need to do is we need to find a way to calculate the flux across that surface. And we're going to use positive orientation, which means that since this surface encloses a solid, doesn't it? So that means we want all our normal vectors to be pointing away from the interior of this solid. So our normal vectors on this paraboloid on the back, all of the normal vectors will be pointing like this, won't they? And then on the green surface, they'll be pointing which way? To the right, yes, like this. All right, that's positive orientation. So now what we do is we determine what we want to call our surfaces. I say we go with S1, S2. All right, so let's talk about S1. Let's call this one S1 and then this one S2. S2 is probably going to take us a little more work, but S1 seems pretty straightforward. Let's see. What do you think about S1? What can you tell me about S1?
Y is the function of x and z.
Okay, so for S1, y is a function of x and z. Do you happen to know that function?
Yes.
What is it?
X squared plus z squared equals y.
If you're saying that y is a function of x and z, then you have to be able to solve this for y, but you don't have y in that equation. Well, we're talking about S1 though, right?
Oh.
S1 was this part. This one has to do with S2, right? So I'm not disagreeing with that. We can look at y as a function of x and z, but what is the function? Y equals 1. Because it's, look, if you're on this green surface, y is 1. Agreed? Okay, so I could do that. That's fine. Now if y is 1, if y is a function of x and z and it's a constant function, then I should be able to use one of these special cases, right? Now, should I write the special cases up here? Do y'all want me to take the 2 minutes to do that? I don't mind doing it. You want me to write them? Okay. So, by the way, for this one right here, there was an additional note. Our normal vectors for this one, which way do our normal vectors have to point if we want to use this special formula? Z is a function of x and y. So that means we have a surface that's like this. Our normals need to be pointing up. What if the normal vectors are pointing down? We change the sign. We just put a negative out here, or we change every one of the signs there. Okay? Let me do the other two over here. Okay, so the other case is if we have that y is a function of x and z, which is the one we're looking at right now, right? Then this becomes the double integral over d of negative p. Make sure you have this right from your notes last class, plus q minus r partial of g with respect to z. Does that look right from last class?
Well, here in the notes you have it as
I know, but I said there was a typo in the notes.
okay.
Remember?
Oh.
Okay. So this should have been the correction I gave you from last time. Now, but here's the thing. Which way are the normals pointing? Which way are the normals pointing here?
To the right.
Okay, so our surface is actually sideways. It goes back towards the surface goes back towards the xz plane. and the normals would be pointing to the right in this, for this formula. Okay? If our normals are pointing to the left, then we have to change everything by a sign. I kind of like that little surface I did there. This comes down to the xy plane, right? And then our last formula, I'll put over here, is if we have what's left? X is a function of y and z. So if we have that, then it becomes double integral over d of p minus q partial g with respect to y minus r partial g with respect to z dA. And in this case, our surface is a function of y and z, so our surface is kind of out here, and it projects back onto the xz plane, x, y, z. So the positive would be out this way, right? Use that formula. Okay, so for S1, what we have this case here, right? And do our normals point to the right? They do, right? Yes. So what I need to do is just take negative p partial g with respect to x, multiply those, plus q minus r. And you know p, q, and r are just the vector field, right? So this is going to be the double integral over d of now p. I need to, is it 0? Yeah, I need to go back up. There's my vector field. So p is 0. So 0 times doesn't matter. But what would the partial of g with respect to x be? Well, here's g, right? It would be 0 anyway, right? So 0 plus, now q. What's q?
0. Oh, no, it's y.
It's y. And then minus r. What's r?
Oh, no.
Negative z. Right? P, Q, R. P, Q, R. And then times what? Partial of g with respect to z. But what's the partial of g with respect to z? 0. All of that dA. Agreed? All right. What's left here? We get double integral over d. And we just get what? Y? How are you getting y?
Yeah. Z times 0.
Yeah, this one's 0, so all that's left is the y. Okay, I agree with this. But what's y? Y is 1, right? When we're on this surface, y is 1. So this is really the double integral over d of 1 dA. It's the area of D, right? What is D? Where though? Like, are you talking about, is D, what were the variables that we were using to describe the surface S1? What were the variables we were using to describe them? X and Z, right? So because we were not using an R of UV, right, to describe the surface, we didn't come up with a parametric representation. It was a special case. Because of that, our domain variables are X and Z. So when we're talking about, this is the area, we know that's the area because we've talked about it for a long time, but it's the area of D, and D is the projection of this surface onto the XZ plane, right? Which would be a circle back here. Understand? That's our D. And so it's the area of that, which turns out to be just the area of that circle. And do we know the radius of this circle? It was 1 because of the inequality here, right? So if the radius is 1, it should just be pi times 1 squared. So it's just pi, isn't it? So this is just pi. Important thing to notice here is that just keep track of what you need to know what this is, what D is in the problem. All right, so S1 wasn't so bad, right? Worked out pretty good. Let's look at S2. What can you tell me about S2? Can we do S2 the same way? Take this out of here. For S2, We have our normals going like this. That, right? And
Y is still a function.
it is. Y is a function of x and z. It's exactly this right here, right? So for S2, y is a function of x and z. And it is exactly the function x squared plus z squared. Did I press record? I did. Okay. All right. And then I can set everything up the same way. What's the difference I'm going to have, though, in this formula? The partials are going to be different, right? And our domain should be the same, because if you take that paraboloid and kind of project it back onto the xz plane, you should have the same circle, shouldn't you?
The vector is pointing in.
That's right, good. The normal vector is actually pointed opposite of this. So when we use this formula, we're going to have to change this to plus, this to minus, and this to plus. Or just put a negative out front. It's up to you. But it's because the normal vectors point in this direction as opposed to this direction. Understand? Okay, so I'm going to go ahead and, do you want me to just put a negative out here and use this, or do you want me to just change those signs? Put it, of course. Yeah, but I'm going to change the signs, because that's what I normally do. I just change the signs. So I'm going to put P, what's P? 0, right? And so it's not going to matter. P is still 0. Partial of g with respect to x would have been 2x, right? And then I'm going to have, instead of plus, I'm going to put minus. And what's q? Y. And then we have, instead of minus, plus r, which is negative z. And then partial of g with respect to z, which would be 2z. dA, and I forgot to put d down here. So this goes away, right? And we have negative y minus 2z squared dA. So that's what I'm trying to do a double integral of. So the domain, right? The domain D involves which variables? In a minute. What variables do the domain involve? X and Z. Because remember, to draw this surface, right? To draw this surface, I am using the variables X and Z. Y is a function of those two variables. So my domain must contain X and Z's. Right? Now, the y here in my double integral, I need to somehow rewrite it in terms of x and z. But I have the equation for y right here. So you know how a second ago we did this problem and we had a y in there and we replaced it with 1 because we were actually sitting on the surface? Here we're going to replace y with this. Okay? With me? Okay, so this becomes double integral over d. That negative is just driving me crazy. So I'm going to pull negative out of both of these, all right? Just put it out here. And can I put x squared plus z squared? That's y, isn't it? That's your y. That's from this. And then plus 2z squared. And then dA. Okay. Questions here? Now what we need to do is figure out what are the domain restrictions on x and z for that surface. If you project that surface onto the xz plane, you would want to do what?
Use R and theta.
You'd want to go to polar, because the shadow of that onto the xz plane is a really good polar. Okay, this is the call I need to take real quick. So why don't you for the polar. X is r cosine theta, and z is r sine theta, right? Do not use x and y because your variables are x and z. And then what are the restrictions you'll have to be able to draw that? Y'all understand we're just projecting this back and drawing that region. 0 to 2 pi. And then r is going to go between 0 and 1. And notice that I didn't put these z squareds together. I did that intentionally because I wanted to make sure you saw what's x squared plus z squared when we go to polar. That's r squared, right? So this is r squared plus 2, and then z is r sine theta, so we square that. So this new integral becomes integral from, I'm going to go ahead and replace things now, 0 to 2 pi. No. Yeah, we usually do radius inside. So 0 to 1 here. And then x squared plus z squared, which is r squared. And then plus 2. And then z, you square the r sine theta, so you get r squared sine squared theta. And then r dr d theta. There you go. And then you would just distribute your r through, integrate with respect to r, then integrate with respect to theta. Think you could handle that? Oh, the negative is still out here. Yes, thank you. That would be important because the answer to this, when you work this out, I'm not going to work it out, but the answer is negative pi. So what is your flux? It's 0. Okay, so the answer to this problem, right, the surface integral of f dot ds over the entire surface is 0. It's the addition of this flux over S1 plus the flux over S2, we get 0. I'm going to save this as, we're going to do this problem in 13.9. When we get to 13.9, we're going to do the same exact problem, and you're going to see that we're going to be able to do it like that. It's going to be super quick, all right? Now, I want to just point something out here. I want to go back to S1. Why didn't we have to do this for S1? Explain that to me again. Like, because what? Because it was 1 dA, right? And that meant the area of the region we're integrating over, right? If it's something other than 1, then you can't do that, right? Okay. But if you go back at S1, we had converted S1 over to a function of x and z, didn't we? We said y equals g of x, z equals 1. Yes? Okay. Could I have done this? Defined it to be r of uv, u cosine v, 1, u sine v, and then let u go from 0 to 1, and let v go between 0 and 2 pi. Would this draw me that green disk? Yes, remember u cosine v, u sine v is going to draw you a disk. And if I fix the y coordinate to be 1, then that would work, wouldn't it? Yes? Okay, so the reason I'm showing this to you is because I want you to see that we could have used this second formula to do this problem. All right? So what would that second formula have said? The double integral over the surface S, not the domain D of our variables, but the entire surface, is equal to F. Now, what's our vector field? 0, y, negative z, dotted with what? The unit normal vector. Okay, so on that surface, we said our normal vectors were pointing out this way, right? And they are pointing out straight that way. So that's really j hat, isn't it? That's the vector 0, 1, 0. The vector 0, 1, 0 is a unit vector, isn't it? So what would happen if I dot this with the vector 0, 1, 0? And then what does it say? ds, right? What is this? Dot, what do you get? Right? You get this? Now what is y? 1, isn't it? It's 1 because of this, right? And what is that integral? The area of the surface S1, isn't it? Yes? I mean, if you want, you can put S1, S1, S1. So we know we're talking about the green one here, sorry. What's the area of the green surface? Well, the same thing as the other one was, right? So we would have got pi here also. Got it? I just want you to see the normal vector in action, because when your normal vectors come out and they look like either I hat, j hat, or k hat, sometimes it's easier to use that formula than it is to actually do one of these. You with me on that? Okay. Yeah, I just kind of went down the road that the first thing I heard, and it worked, right? Okay, let's move on. All right, find the flux over the vector field. So we have an more interesting vector field, x squared, y squared, z squared, across the surface S, where S is the boundary of the solid half cylinder. Z is between 0 and square root of 1 minus y squared, and x is between 0 and 2, and it's everything in between. So you can kind of see the, I don't know if you can see it here. There's the origin, and then you have the z-axis comes up, and then you've got your x-axis coming out at you like this, like that. And it's a cylinder, but it's only half of it. And you can kind of see that from this inequality right here. If you were to take that, turn it into an equation instead of an inequality, and square both sides, and then move the y over. This is your cylinder of radius 1 coming out the x-axis, right? But because we are algebraically writing it like this, it's only the positive z values, so you don't get the bottom half of it. Y'all good with that? Sure? So we have how many surfaces here?
3.
We have 3? 4. We have this front side, the back side, the bottom side, and then this green dome-ish thing, right? All right, so let's start attacking these. Let's call this one S1. The back one, let's call that S2. The bottom one, let's call it S3. And then this one, we'll call it S4. All right. Let's go after S1 first. For S1, I could say for S1 that x is a function of y and z, or z is a function of x and y, or y is a function of x and z. What can I use there for S1? X is a function of y and z. In fact, x is which function? We know exactly what it is, don't we? So your x values are between where and where? 0 and 2. So 0 is the back side, isn't it? And 2 would be this front side. So that's just the equation x equals 2. Y'all agree? Now, do you want me to continue with this and use a special case, or you want to try that normal vector thing? Let's try the normal vector thing. I like the idea of the normal vector thing for this particular reason. If I use the normal vector thing, I know this normal vector. They come out at me, right? They're coming out like this. And that normal vector is the vector 1, 0, 0. That's a very easy vector to work with. So let's use that formula. The flux over S1 should be F dot the normal ds. So what would happen if I take the vector field, x squared, y squared, z squared, and I dot it with the normal vector 1, 0, 0, ds. All I'm left with is what? X squared, right? So this is integral over S1 of x squared ds, which is, what's x? 2. Because we're on S1, x is 2, right? That's a good thing. Because that's just double integral over S1 of 4 ds. I can pull the 4 out. And this is 4 times double integral over S1 ds, or 1 ds, right? This right here is the surface area of of S1. Do you know the surface area of S1? It's half of the circle's area. And what's the area of that circle? Because the radius here, can you tell? The radius is 1. You get that from, I erased it. Remember when I solved that little thing and I said you get y squared plus z squared is 1? That's where you'd get that circle radius of 1. So what is the area of just this pinkish thing? Pi over 2, right? Pi over 2, but then times 4. So you're going to have 4 times pi over 2, which is 2 pi. Okay, so if the flux across S1 is 2 pi. Save that. We'll need that later. Got it? All right. Question?
For S2, would it be the same thing, just in the negative direction?
For S2, well, kind of, but we're not going to get negative 2 pi, though. It's because of, well, let's do it, okay? Remember how we got 4 here? How did we get 4 here? Because x was 2. When we move to S2, what's x? 0. So it's actually going to 0 the integral out. But let's do it. S2, x is still a function of y and z, but it's actually the 0 function. We still want to do this dot over S2 now. And then over S2, we dot this. This is all still the same, isn't it? This normal, though, is negative. Thank you. Because it's not I hat, it's negative I hat. It's pointed out the other way. Right? Remember that normal's out the backside. Right? That normal for S2. So when we dot it, we'll get, what, negative x squared here? But what's x? 0, so we get 0 here. Understand that? And so the answer is 0. I got an interesting question the other day from a student that I think is worth me just mentioning real quick here. Because, okay, what is the derivative of a constant? 0, right? So the antiderivative of 0 should be a constant, right? So if I take the antiderivative, let's go integral from like 2 to 4 of a constant dx, this is old school like Cal 2, then what should my answer be? Well, what's the antiderivative of c? Cx, evaluate it from 2 to 4, right? Or 4 to 2, however we want to say that. Plug in 4, what do you get? 4 times c, right? You get 4 times c minus 2 times c. So that's just 2c, right? So it would be twice the constant. So what happens if you take integral from 2 to 4 of 0 dx? It's going to be 0. But the reason why is because the constant you're using is 0. So when you go and you do this formula, right, what's the antiderivative? What's the antiderivative of 0? No. What's the antiderivative of 0? A constant, right? I'm going to call that constant k. All right, so you don't mix it up with this c. Now you're supposed to evaluate what? K from 2 to 4, right? What happens when you plug in 4? You don't, yeah, this doesn't have x in it, right? So when you plug in 4, what do you get? K. When you plug in 2, what do you get? K, and k minus k is 0. That's why you get the antiderivative of 0 is 0. It's because the result, the antiderivative, is a constant. And when you evaluate a constant at 2 different points, it doesn't matter because the constant's the same. So when you subtract them, you get 0. Do not confuse that with this case. The antiderivative of a constant is c times x. Although this formula still works, right? If c is 0? Because you get 2c and 2 times 0 is still 0. So you get the same answer. All right, let's move on. All right, so now let's go to S3. S3 is the bottom one. So what can you tell me about S3? So it's just the bottom of this, right? That's z is a function of x and y. And what is that function? 0, because we're on the xy plane. And this has been working out really good so far with these normal vectors. On these flat surfaces, these normal vectors are kind of nice to work with. So I have a vector pointed out the bottom here. That normal vector is the vector 0, 0, negative 1. And I'm going to just take that, and I'm going to dot the vector field with that 0, 0, negative 1 ds. And all I get here is negative z squared, right? ds. Guess I didn't need the parentheses, but. And what is z on this surface? It's 0. So you get 0 here. So far, on S1, S2, and S3, the flux is what, 2 pi? Okay, now we need to do S4. S4 is more complicated. And we cannot use the method we've been using here. Because here, that normal vector is the normal vector for any point on that surface on the back, right? And then this one that we used on the front, when we said the vector was 1, 0, 0, it doesn't matter where I am on that surface, it's always 1, 0, 0. But when I'm on the green one, as I move along the surface, my normal vector is changing. So it's not as clean as that. I think we'll have to use this one of the special cases. Or we're going to have to get it as a parametric function of u and v and do this cross product. But remember, the whole idea behind the short formulas is so that you don't have to do the cross product of the partials. If you want to, feel free. You can do it. Nothing wrong with it. If we had more time, I'd probably show you both ways. I do it without the shortcut and with the shortcut, just so you could see the two in action. But for S4, I'm going to be able to write S4 that what is a function of what? Z is a function of x and y. So it's kind of like the green one is kind of like the standard surface, isn't it? The ground is the domain. And what is that function? Root 1 minus y squared. Okay. Now, since I'm using this one, and my normals, they don't point straight up, do they? Right? But do you agree that if I'm on the green surface, do you agree that the k component, or the third component of the normal vector, is positive? So I'm going to, whatever this vector is, it's going up a little bit. It's not going down. That's what we mean by this shortcut. When we say the normal vector is up, we don't mean necessarily straight up. We just mean it's got more of an upward component than it does a downward component. So this is going to be the formula we use. We don't change anything to negative. Does that make sense? Okay. So I'm going to use that formula. It's going to be the double integral over d. What are the domain variables we're going to be using here? X and y. Okay. And then I'm going to do negative p. So what's negative p?
0.
Negative x squared times the partial of g with respect to x. I don't have an x, so 0. All right, now minus q. Q is y squared, but then partial of g with respect to y. Ooh. You have to take derivative of that with respect to y. So 1/2, that to the negative 1/2 drops down. Then derivative of the inside is negative 2, and that kills off the 1/2. So if you take the derivative of this, you should get like negative y over the square root of 1 minus y squared. So this is like the worst derivative we've had, for these problems. That's it right there. Everyone okay with that as a derivative? And then we have plus r. And what's r? Z squared. All that dA. All right, let's try and clean this up a little bit. This is 0, double integral over d. And we've got, when we put these two together, and it's negative and negative, it's positive. So we've got y cubed over square root of 1 minus y squared. And then plus, what were my domain variables again? x and y, but I've got a z here. So I've got to replace that z with this, right? So replace it, take that, square it, and you just get 1 minus y squared. dA. All right. Unfortunately, this is not 1, right? So this is not just the area. Well, what if it was the area of, oh, d of d? We'd be okay. Because what is d? Do y'all see d here? D is the ground, isn't it? It's the rectangle on the ground. That's your domain, because the domain is the part that's, the domain variables are x and y, so our d is going to be in the xy plane. Do you have an easy way of representing that domain? Yes? It's just two constants, right? Like your x's are stuck between constants, your y's are stuck between constants. So we can go right away to this. This should be the double integral. Let's do the outer integral. Let's let the outer integral be x. So what are the restrictions on x for this rectangle on the ground? 0 back here to what? 2, right? 0 to 2. And then, what?
This is if it was 1 dA, right?
If it was 1, what? No. I'm not. What I'm doing, because I can't do 1 dA, I actually have to set up my limits of integration. My limits of integration are going to be the restrictions I have on my domain variables, which are x and y. And in order to draw this green surface, right, up here, you can only plug in points that are down here on this rectangle. So right now, my x's have to be between 0 and 2. And what about my y's? Negative 1 to 1. Is that clear? Eric, you good with that? Okay. And then this, right? Any other questions? I'm getting some kind of sketchy looks out there. It is Monday, but it's almost over. Well, you got to take finals and stuff. It's almost over for me. Okay, we good? All right, we have to integrate that. Let's do it. I figured you'd want to have the pleasure of integrating that. Nope. The question was, would this have been better had we defined that green surface with R of UV instead? We would have basically got to the same point, except we would have it in terms of U and V, and the integration would probably be just as bad. Yeah. But, I mean, the integration's not terrible. I mean, we can integrate these two, right? That's not really worth talking about. It's really just this one right here. So let's talk about how, I'm doing scratch work, I'll come back to this. If I asked you to integrate or find the antiderivative of this, what could you do? Trig sub? You could do a trig sub. I'm kind of scared to do a trig sub, though. We could do it. Okay, so I'll give two options here. This can be done with trig sub. The other option is it can be done with a U sub. You just have to be a little bit clever with the U sub.
Would you have to split apart your y cubed on the top?
Yeah, exactly. So let's say that we picked 1 minus y squared to be our U. The derivative of that would be like negative 2y, which we have more than that, right? We have y cubed up there. But if we split it, then you would have a y, and then you'd also have a y squared. But I have an equation that has y squared in it, right? So look, this is what I mean. If I do this, like that, and then I say du is negative 2y dy, then if I solve for y dy here, I get negative 1/2 du is equal to y dy.
Y squared is u plus 1.
Yeah, so we're going to go back over here. We're going to rewrite this y squared over square root of 1 minus y squared y dy, kind of peeling off one of the y's, so that y dy can be replaced with negative 1/2 du. And then this 1 minus y squared will be replaced with u. And all I need to do is figure out what y squared is. But if you take that and solve for y squared, you get y squared is 1 minus u. Right? Or you're looking at them going, did I take Cal 2? I think I took Cal 2. OK, so y squared is 1 minus u. The denominator is root u, right? Root u. And then y dy is going to be negative 1/2 du. So I'll pull the negative 1/2 du out like that. Now, is that any better? What can we do with that? Separate them, right? You have two terms in numerator and one in the denominator, so just split it up into two different terms. So that would become negative 1/2 integral, and you would have 1 over root u, right? Which would really be u to the negative 1/2. And then you'd have minus u over root u, which would really be u to the positive 1/2. And then we could just set these up for power rule now, couldn't we? Just the antiderivative. So this would be negative 1/2, and now I'm ready for my antiderivative. It would be antiderivative of this, 2u to the half. So you're adding 1 to the power, and then out front you have to do 1 over that, and flips up. And here you get minus 2/3 u to the 3/2, right? That would be the antiderivative. But then plus c and all that junk. But you would have to now switch back. What was u?
1 minus y squared.
Yeah, so let me write the final thing here. We're going to have negative 1/2 and then 2. This right here gets replaced with 1 minus y squared, and that's square root. So I'm going to just write it that way, square root of 1 minus y squared. And then this one right here is minus 2/3. And then this one is, you could do square root of 1 minus y squared if you want, but then cubed. That's what that means. So that's the antiderivative of this, OK? Sorry, just this. I still have to do these two, right? All right, so now I'm going to continue this. This is equal to do I have to do what once? I only have to, well, I'm going to have to integrate with respect to x after this, but only with respect to y one time. OK, so I'm going to have the outer integral 0 to 2, and then the inner integral, right? This right here turns out to be, and let me distribute this constant through. Is that all right? So this is going to be minus this root, minus square root of 1 minus y squared, and then plus what? 1/3, and then square root of 1 minus y squared, but that cubed. That's the antiderivative of this, plus y minus 1/3 y cubed. So that's my antiderivative of everything in here. I'm going to evaluate that where? Right? Y is negative 1. I'll put y. Y is negative 1 to y is 1. And after I'm done with all that, I'll have to integrate that with respect to x. And it looks bad, but it's not. It actually works out really nice. Because when you plug in 1 here, 1 squared is 1, you get 0 here, right? You get 0 here. So those are gone. When you plug in 1 here and 1 here, you just get 1 minus 1/3, which is 2/3. So this is going to be integral 0 to 2, still working in here. When we plug in 1, we got 2/3, right? Minus, now let's plug in negative 1. Negative 1 here, square, you still get 0. Negative 1 here, you still get 0. Negative 1 minus, now negative 1 to the third power is still negative 1, so it'll be minus a negative 1/3, so plus 1/3. Like that. And then dx. So we have 2/3, and then it's going to wind up being plus 2/3, which is 4/3, right? So this is integral from 0 to 2 of 4/3. It's a constant. Isn't that nice? The antiderivative of that with respect to x is what? 4/3 x. And then you evaluate 0 and 2, and you should just get 8/3. So what is the flux over this surface? The flux over the entire surface of f dot ds for this problem is, we had 2 pi from earlier, right? S1 gave us 2 pi. S2 gave us 0. S3 gave us 0, right? So we have 2 pi plus 8/3. Here we go. I will also do this problem in 13.9, and we're going to do it in about 30 to 40 seconds, and you're going to be all mad. And then you'll be happy because you'll see that how powerful the divergence theorem really is. All right. What do y'all think? Does your cuppeth overfilleth yet? Yetteth? There's the homework.
Professor,
Yes.
so on the test, will you specify which way you want it to be done?
The question is, on the final, am I going to specify how the problem is to be done? I will not. Okay, now I know that sounds good, but that also means that you need to know what to do. And so, like, I want you to be able to do one of these formulas and not just do the divergence theorem. And the way I'm going to do that is by giving you a surface to calculate the flux over that's not closing in a solid. See, divergence theorem, as we'll see, only works if you enclose a solid. So if you look back at these examples that I did in this section, the last 3 I did were over solids. Wait. But this example that we ended class with last time was just a surface, and you could not use divergence theorem on that. Okay, so if you get something like that, you have no choice but to, use either this or this, which means you have to draw the surface yourself, or realize it's one of these special cases. That's how I'll force you to do one way or the other. Same thing with line integrals. Like, you're free to use Green's theorem, but you can only use it on closed loops. So if I give you a curve that doesn't close, you can't use it. It's a good question.
Number 5 through 31 on.
There you go. It's a lot of problems, actually. But this section includes surface area. Is it? I believe it's surface area, surface integrals, and flux. So there's like stuff we covered like 2 classes ago are in this. All right, we're ready to start 13.7.
Is this demonstrating?
I meant 13.8. Yep, that's what I meant. That was 13.7.
Is this a super short one?
This is another shortcut, yes.
No, I mean, like, is it the short one you were talking about?
No, it's not the super short one. That's 13.9. That's divergence theorem. All right. This, the way you say this is Stokes' theorem, not Stokes' theorem. Although people argue about how to say it. Stokes' theorem. All right, so let me remind you of a theorem that we had in R2. If you're trying to do the line integral over a closed curve of f dot dr, that was referred to as work. You have a vector field. You have a closed curve. I forgot to put C. You've got this closed curve, and you're moving along this curve. We orient this counterclockwise as positive orientation. We have this C. We've got this vector field everywhere, right? And you're moving through this thing. Right? You got it with me? Yes? This looks familiar? And we had this wonderful theorem that said that instead of worrying about going across the line integral, that you could look at the region inside, call it R, and you could use, this was Green's theorem, right? And it said that this could be converted to, this could be turned into the double integral over R, and then it was something weird. It was like partial Q with respect to X minus partial p with respect to y. Remember that? dA. That look familiar? So remember, the vector field that you're given here, F, right? F was the vector field PQ. There is no R. Why is there no R? I'm in two-dimensional space, right? I'm in two-dimensional space. So think about this for a second. If you draw a closed loop, right? Do you agree that no matter how you draw it, there is really only one R that we can be talking about here? Like there's only one region possible. And that region inside, that region is a surface. It's on the flat sheet of paper here, but it is a surface, isn't it? Okay. Stokes' theorem is a generalization of Green's theorem into three-dimensional space. That's what the theorem is. So let me show you the theorem, but I want you to understand it's basically this idea moved into 3D. Maybe we should look at the idea before we actually look at the theorem. Stokes' theorem is going to tell us this. If you're in R3 now, and you've got a vector field, PQR, and you've got a closed loop in three-dimensional space. Three-dimensional space. So remember, this loop is in 3D. So wherever you're like X, Y, and Z axis, just imagine it's like a fly flying through this room, right? Like a fly takes off from here, flies around, and then comes back, all right? Then that's our curve C. Stokes' theorem gives us a way of evaluating the line integral. Okay, the line integral, the same thing we had earlier, which was work. But it does it by making us look at the surface that this loop encloses. That should be problematic in your mind right away. What's problematic with that? Okay, direction, that's one consideration we have to think about, direction. But what else? If I draw this loop, I said there's only one surface we can talk about here, right? So think about the surface between there. So try and do an example here. Yeah, okay, so we'll use this as a surface. In three-dimensional space, let's say that this is the closed path that we're going to go around, right? Like let's say this is C. Then this surface right here would qualify as a surface that has this curve as its boundary. Agreed? But imagine this were made out of like a really thin membrane, really thin, so I could maybe push it up and put a little bulge in the middle of it. But the boundary stays the same. Okay? So I deform the inside of it, but I still have the same boundary. Right? Stokes' theorem tells us that you actually can still get the correct answer, and it does not matter what the surface inside is doing, as long as the boundary of the surface is